Picture this. You are 100 meters underground, right on the border of France and Switzerland.
Yeah, deep under the countryside there.
Right. And there is this massive 27-kilometer circular tunnel. I mean, it's literally big enough to run a commercial train right through the middle of it.
Oh, easily. It's a massive physical space.
And down in this tunnel, it is maintained at a temperature that is actually colder than the vacuum of deep space. But here's the wild part. At very specific points inside that freezing ring, humanity is routinely generating conditions that are hotter than the center of the sun.
It sounds like science fiction, honestly.
Yeah.
But it's very real.
It really does. And the goal here isn't just to, see what happens when things get super hot. The mission of this deep dive is to explore why scientists are using this machine to do something that sounds almost like ancient mythology. They're trying to recreate the first microscopic fractions of a second right after the Big Bang.
Exactly. I mean, we are talking about the largest, arguably the most complex machine our species has ever engineered. The Large Hadron Collider, operated by CERN.
The LHC.
That's right, the LHC. And what it does is it takes the absolute smallest pieces of matter, accelerates them to 99.999999% of the speed of light, and then deliberately crashes them head on.
Just smashing them together at unbelievable speeds.
Smashing them together, yeah. And the motivation driving all this extreme engineering is a quest to answer really the oldest question we have, which is, what is the universe actually made of?
Which is such a massive question. So, okay, let's unpack this a bit, because if you were listening to this, you might be wondering why thousands of physicists and billions of dollars are poured into an underground freezer just to smash things. We first have to clarify what it is we are actually smashing.
Right, the ingredients.
Yeah. So the name Large Hadron Collider kind of gives us the first clue. A hadron is basically a composite particle, and the specific ones they use most often are protons.
Protons, yes. The workhorses of the collider.
Right, and you don't need a background in quantum physics to know what a proton is. They're the basic building blocks sitting in the center of every single atom, including, the ones making up the device you're listening to this on right now.
Exactly. But what's fascinating here is that by choosing protons, scientists are deliberately choosing a very messy collision.
Messy how? Like, they aren't just solid little spheres.
No, not at all. A proton is not a solid uniform ball. It is essentially a tiny, chaotic bag of even smaller particles called quarks. And those are held together by these things called gluons.
Okay, so it's a bag of smaller stuff.
Right. So when you throw two of these composite bags at each other at almost the speed of light, you're guaranteeing an incredibly violent, incredibly complex interaction. You aren't just, bumping two billiard balls together.
You're initiating this catastrophic disruption of matter.
Exactly. A fundamental disruption.
And that disruption brings us to the core mechanism of the whole project, which hinges on Einstein's famous equation, E equals mc squared.
The most famous equation in the world.
Right. And that equation basically tells us that energy and mass, they aren't two separate things. They are two forms of the same exact thing.
Right. They can be converted back and forth.
Yeah. So this collider, it isn't just a giant sledgehammer trying to crack open a proton to see what's inside. It is, quite literally, an engine of creation.
Yes. And that distinction is crucial. It completely changes how we view the machine.
Mm-hmm.
Because when those two protons collide, an astonishing amount of kinetic energy, which is just the energy of motion, is suddenly concentrated into this tiny microscopic point in space.
Just a massive amount of raw energy in one spot.
Right. And because of the rules governing our universe, that concentrated energy doesn't simply vanish. It has to go somewhere, or rather, it has to become something.
Okay, so I was thinking about how to explain this, and it's kind of like, imagine crashing two perfectly normal sedans together at top speed.
Okay, I like where this is going.
Right. But instead of just getting crumpled car parts and glass everywhere, the energy of the crash is so intense that a brand new glowing spaceship just pops out of the explosion.
That is a brilliant analogy, actually. Because normally, if you strike an anvil with a hammer, the kinetic energy from your swing just dissipates.
Yeah.
Right? It becomes a loud noise and a little bit of heat.
Right, just bleeds off into the room.
But inside the LHC, there is so much kinetic energy focused into such a tiny, localized point that it can't just dissipate as heat. Instead, that raw energy literally freezes into entirely new physical matter.
It conjures it out of nowhere.
It conjures brand new exotic particles into existence that absolutely were not there before the impact.
That is just wild to me. It's essentially magic, but it's physics.
It really is. And these particles generated from that raw energy, they are highly unstable. They're incredibly heavy, and they are definitely not the kind of matter you find just floating around in the modern universe today.
Right, because these are the original ingredients of the cosmos, right?
Exactly. By generating these particles, scientists are basically rolling back the clock. You see, as the universe expanded over billions of years, it cooled down. And those heavy early particles, they decayed into the stable, boring matter we see today.
The stuff that makes up us and the planet.
Right, so if you want to study the original fabric of reality, you have to build a machine capable of baking those original ingredients all over again.
Okay, but here's where it gets really interesting. Because to recreate those primordial Big Bang conditions, you can't just set up like a standard laboratory laser on a desk. You need a machine that creates conditions more extreme than almost anywhere else in nature.
The engineering constraints are just mind-boggling.
They really are. Like, for starters, you have to condense these protons into a beam that is thinner than a single human hair.
Thinner than a hair, yeah. And it's actually two beams traveling in opposite directions around that 27-kilometer track. And they are circling millions of times every single second.
Millions of times a second. Keeping a hair-thin beam of particles perfectly on track at that speed just sounds impossible. I mean, you can't just build a metal tube for them to travel through, right? Because they would just instantly drift and smash into the walls.
Right. Any physical contact and the beam is lost. You have to steer them without touching them at all.
So how do you wrangle moving charged particles without touching them?
Magnets. It's the only way. Thousands of massive, incredibly powerful magnets line the entire perimeter of the tunnel, and their whole job is to constantly push, pull, and focus those protons, guiding them perfectly along the curve of that underground track.
Okay, but the faster the protons move, the stronger the magnetic field needs to be to keep them from just flying off in a straight line, right?
Exactly. And to bend a beam moving at 99.9999999% the speed of light, standard magnets aren't going to cut it. You need a magnetic field so intense that if you tried to run the necessary electrical current through, say, standard copper wire,
You just melt.
oh, instantly. The electrical resistance would generate enough heat to vaporize the wires and probably a good chunk of the machine along with them.
Wow, so they use superconducting magnets.
Yes. Superconductivity is this incredible state where a material conducts electricity with absolutely zero resistance. No friction, no heat, just a perfect, unimpeded flow of energy.
But the catch is, materials only achieve that superconducting state under extremely specific freezing conditions, right?
Very freezing. The entire magnetic ring is encased in a cooling system that pumps thousands of liters of liquid helium around the wiring. This drops the temperature of the magnets down to 1.9 Kelvin.
Which is just a fraction of a degree above absolute zero.
Exactly, the theoretical limit of coldness in the universe where all atomic movement basically stops.
See, that juxtaposition is what blows my mind. You have these localized collision points inside the machine, generating temperatures hundreds of thousands of times hotter than the center of the sun, and those microscopic infernos are surrounded by magnets chilled colder than the void of deep space.
And that extreme cold is the absolute fundamental prerequisite for controlling the extreme heat. It's a delicate balance. If a magnet warms up by even a single degree, it undergoes this process called a quench.
A quench. What happens then?
It loses its superconductivity, resistance returns instantly, the heat spikes, and the massive magnetic field just collapses. The beam would be lost in a fraction of a second.
That's terrifying. The precision required to maintain that environmental balance across a 27-kilometer ring is just a monumental achievement.
It really is one of humanity's greatest engineering feats.
So all of this precision, the hair-thin beams, the liquid helium, the crazy electrical currents, it's all orchestrated to force these two beams to cross paths and collide head-on at specific points.
Right, at a handful of very specific points around the track where we have detectors waiting.
And calling them detectors feels like a massive understatement. These are subterranean structures the size of cathedrals, right? Just packed with layers of sensors.
Cathedral-sized is accurate. They are gargantuan digital cameras, essentially.
Okay, but when the beams cross and that energy freezes into new exotic particles, how do these giant cameras actually see anything? Because the new matter doesn't just hang around to pose for a picture, right? It decays almost instantly.
Right, it falls apart incredibly fast. So they don't actually look for the exotic particles directly, they look for the shrapnel.
The shrapnel.
Yeah, as those heavy, short-lived particles decay, they explode into a cascade of lighter, more stable particles that blast outward through the layers of the detector. And the detectors build kind of like an onion.
Okay, layers of sensors.
Exactly. The innermost layers are silicon, tracking the electrical charge of the passing particles. Outer layers measure the energy absorbed as the particles are stopped.
So it's essentially forensic reconstruction. By looking at the speed and the trajectory of all that microscopic shrapnel, they use supercomputers to trace the lines backward to the exact point of impact.
Bingo. They calculate the mass and properties of whatever materialized in that 1/1,000,000th of a second before it exploded.
That is unbelievable. And this forensic capability, this is what the whole physics community spent decades preparing for, right? Because they had a very specific target in mind.
They did. It was a massive, decades-long treasure hunt that culminated in 2012 with the discovery of the Higgs boson.
The famous God particle, though I know physicists hate that name.
They really do despise that name, yes.
But if you're wondering why they spent billions hunting for this one specific particle, it comes down to a glaring hole in our basic understanding of reality.
Right, the standard model.
Yeah, the standard model, which is basically the instruction manual for all the fundamental particles and forces in the universe. But for a very long time, this manual was missing a really crucial chapter.
It was. The math of the standard model was incredibly accurate at describing how particles behave, but it couldn't explain one fundamental property, and that property is mass.
Why things weigh anything at all.
Exactly. The equations couldn't answer why a quark inside a proton is heavy, while a photon, which is a particle of light, has absolutely zero mass and just zips around at the speed limit of the universe. If everything is just a fundamental particle, why do some have weight while others don't?
Right. So nearly half a century before the LHC was even built, theorists came up with this radical idea. They suggested that the universe isn't just empty space. They theorized that everywhere, in every corner of the cosmos, there is this invisible, undetectable field permeating all of reality, the Higgs field.
Right. And to visualize how this invisible field actually gives things mass, let's use an analogy. Imagine moving through water.
Okay, like wading through a swimming pool.
Yeah. If you were trying to walk through waist-deep water, you have to push through it. The water drags on you, it slows you down, it makes you feel heavy and sluggish.
It takes effort to move.
Exactly.
Yeah.
But if you compare that to moving through the air, you don't feel that drag. You just move freely.
So the drag in that scenario is how we can conceptualize mass.
Precisely. The theory proposed that particles gain their mass solely based on how much they interact with this invisible Higgs field. A heavy particle interacts with the field deeply, so it feels a massive amount of drag, like walking through water.
Okay, and a particle of light.
The photon doesn't interact with the field at all. It feels no drag, like moving through empty air, and therefore it has absolutely no mass.
It just coasts right through. That is a brilliantly elegant theory, but I mean, in science, an elegant idea isn't enough, right? You have to actually prove it.
You do. And the problem is you can't see this field. You can't touch it. You can't measure it directly with a thermometer or a ruler.
Right, it's totally invisible water. But the mathematics offered one testable prediction.
Yes, the prediction was that if you hit this invisible field with enough concentrated energy, it would ripple. And if you jostle the field hard enough, that localized vibration would actually manifest as a distinct particle.
And that particle is the Higgs boson.
That's the one.
So let me make sure I have this straight. We couldn't see the water of the universe directly, but by smashing protons together at near light speed, we basically made a massive splash. And that splash is the Higgs boson.
That is a fantastic way to put it. Yes, we forced the field to reveal itself by making a splash. And the stakes here were monumental.
Because if they didn't find it,
if the machine ran at full power for years and failed to produce the Higgs boson, it would indicate that our entire foundational framework for how reality operates was deeply, fundamentally flawed. Decades of physics would just have to go straight back to the drawing board.
Talk about pressure. But in 2012, after sifting through the shrapnel of hundreds of trillions of individual collisions, 2 of those cathedral-sized detectors spotted the signature.
And they were operating completely independently, too, to ensure they didn't bias each other's results.
Right, which makes it even more incredible. They both found the exact same ripple. They proved the Higgs field is real.
It was an absolute triumph. It finalized the standard model and, of course, earned a Nobel Prize for the theorists who had predicted it 50 years prior.
Now, finding that ultimate missing puzzle piece might sound like the end of the story. You might assume the physicists just, packed up their superconducting magnets and went home.
Far from it.
Right, because finding the Higgs actually highlighted just how much of the universe we still do not understand. I mean, the standard model might be finished, but it leaves out some truly massive elements of reality.
The most glaring omission being dark matter.
Right.
Astronomical observations show us that there is this mysterious, invisible substance out in the cosmos that outweighs all the ordinary visible matter, the stars, the planets, us, by a staggering margin. And the standard model has no particle that accounts for it.
It's just entirely missing from the math.
Completely. Furthermore, the model totally fails to incorporate gravity, which is literally the most ubiquitous force we experience every single day.
So that's why the collider didn't shut down after 2012. Scientists are continually upgrading it, cranking up the energy levels, looking for entirely new particles that could explain dark matter or bridge that gap with gravity.
Exactly. They are actively looking for cracks in their own theory.
But so far, nature's being pretty stubborn, right? No new surprises have really popped up.
It is stubborn, yes. Despite the higher energy collisions, no wild new particles or physics-breaking surprises have materialized. The standard model is holding its ground flawlessly.
Which, to an outsider, running a multi-billion-dollar machine and finding nothing new sounds kind of like a failure.
I get why people think that, but in particle physics, a null result is actually a profound result.
Really? How so?
Because the stubbornness of nature provides essential boundary conditions. By meticulously proving that new particles do not exist at these specific energy levels, the collider systematically narrows down the hiding places for new physics.
Ah, okay, so it tells you where not to look.
Exactly. It forces theorists to abandon dead-end ideas and invent entirely new mathematical approaches.
That makes sense. Though, pushing the boundaries of known physics to hunt for unknown forces, it understandably causes some unease for people who aren't quantum physicists. Which, we have to talk about this, brings us to the public panic from the late 2000s, right before the machine powered on.
Oh, the doomsday scenarios.
Yeah, I remember this so clearly. There were lawsuits, protests, major news headlines claiming the LHC was going to trigger the end of the world.
The primary fear was that focusing that much energy into a microscopic point could accidentally generate a miniature black hole.
Right, and the narrative was that this tiny black hole would just sink to the Earth's core and swallow the planet from the inside out, which, even if you like science, the phrase manufacturing a black hole underground is definitely going to trigger some primal anxiety.
It sounds alarming, absolutely.
So how do you definitively put the listener's mind at ease? How do we know this machine won't just end the world tomorrow?
We just point to the sky, really. The debunking of that whole scenario relies on cosmic rays. You see, our universe is constantly operating as a giant, naturally occurring particle accelerator.
Just constantly smashing things together on its own.
Exactly. For 4.5 billion years, high-energy particles from exploding stars and active galaxies have been slamming into the molecules of Earth's upper atmosphere.
And those natural collisions happening above our heads, they are occurring at energy levels far exceeding anything we could ever generate inside the collider, right?
Far exceeding it, yes.
Mm-hmm.
Nature has been running this exact same high-energy collision experiment billions of times a second for the entire history of the solar system. And our planet remains firmly unswallowed by black holes.
Still here.
Still here. The collider isn't doing anything unnatural. It is merely recreating these naturally occurring atmospheric collisions in a highly controlled underground environment, where we happen to have specialized digital cameras waiting to record the aftermath.
That is so reassuring to hear spelled out like that. But, looking past the microscopic physics and the debunked black hole panics, there is an entirely different reason to marvel at this collider. And it has to do with the species that actually built it.
The human element.
Yeah. We are talking about a laboratory designed, constructed, and operated by thousands of scientists, engineers, and technicians from dozens of different nations around the globe.
It operates continuously across geopolitical borders, across language barriers, and deep cultural divides.
And what I find so exceptional about it is the complete lack of a conventional payoff. There's no military application for a Higgs boson.
No, you can't weaponize the fundamental laws of mass.
Right, and there's no commercial product to patent and sell to consumers. The absolute only reason all these rival nations pooled their massive budgets and their brightest minds is just this collective desire to understand nature, to satisfy human curiosity.
And that collaborative effort, it extends way beyond the physical tunnel in Switzerland. This raises an important point about the data itself. When the beams are crossing, there are up to 1 billion individual proton collisions happening every single second.
1 billion a second?
Yes. and the sensors produce a torrent of raw data that would fill thousands of commercial hard drives every single day. No single supercomputing facility on Earth could possibly process or store that much information.
So how do they even sift through all that noise to find the shrapnel of something like a Higgs boson?
They built a decentralized global infrastructure. It's called a worldwide LHC computing grid. The data from the detectors in Europe is instantly beamed out to a tiered network of over 170 computing centers located in more than 40 countries.
Oh, wow. So it's a massive distributed network.
Exactly. Institutions from all around the world take fragments of the data, crunching the complex mathematics collectively.
That is just beautiful. It proves that human knowledge scales exponentially when we actually choose collaboration over competition. In an era where so much of the modern world just feels hopelessly fractured, you have tens of thousands of people seamlessly sharing petabytes of data purely for the sake of discovery.
Knowledge really is most valuable when we collaborate. The LHC stands as a monument to what humanity can accomplish when we unite behind a shared question.
It really does. So to recap the scope of what we've explored today, we started with a 27-kilometer cryogenic ring buried deep underground, navigating the absolute extremes of cold and the blazing heat of the early cosmos.
We looked at how kinetic energy crystallizes into brand new matter.
Right, tracking that microscopic shrapnel to finally prove the existence of an invisible field, the water of the universe that gives everything its mass. And we saw how a global network of humans works in pure harmony to process the secrets hidden inside a single proton. All of this to answer one simple question. What is the world made of?
It is the ultimate refusal to stop asking what lies one level deeper.
Which leaves us with a final thought for you to mull over. The collider is still running. It's still hunting for that invisible dark matter holding our galaxies together, still searching for the missing pieces of gravity. But let's imagine a future where the machine succeeds completely.
Okay.
Let's say we finally complete the standard model, we find the dark matter particles, and we map out the absolute final laws of physics. Will that actually be the end of the scientific journey? Or, by cracking those ultimate mysteries, will we simply realize that our grand, finished puzzle is really just one tiny corner of an even larger, entirely different game we haven't even begun to conceive of yet?
Given the history of science, there's almost certainly a deeper layer waiting to be found.
Always another layer. Thank you for joining us on this deep dive into the absolute limits of human engineering and cosmic knowledge. We'll leave you to think about that invisible field giving weight to the world all around you.
Bye.
Until next time.